In this section, we're going to look at reaction mechanisms. And the mechanism of a reaction, as it says, is just the pathway of the reaction from its reactants to its product. We're going to start by looking at the reaction shown. Nitrogen dioxide plus carbon monoxide goes to nitrogen monoxide plus carbon dioxide. Experimentally, the rate equation, the rate law, was determined to be K equals the concentration of NO2 squared. Chemists proposed the following mechanism for this particular reaction. First step, NO2 plus NO2 goes to NO3 plus NO. Second step, NO3 plus carbon monoxide goes to NO2 plus CO2. Now if you add these two steps together, you should get the overall reaction. Just like Hess's law, it does work. It turns out when we're doing mechanisms, we have a couple of things to consider. Each of the steps above that we wrote out in green is called an elementary step. The elementary steps, again, are proposed. They're theoretical. The elementary step rate depends on the reactants and the coefficients of the reactants. So if we were to write a rate law for each elementary step, it would look like this. For the first one, the rate equals K1 times NO2 squared, because essentially the reaction is 2NO2, which is equivalent to NO2 plus NO2. For the second reaction, rate equals K2 times the concentration of NO3, first order, concentration of CO, first order. So, elementary steps are proposed for an overall reaction. Those are the mechanisms, and the rate for each elementary step is simply the reactants, and each coefficient for a reactant becomes the order of that reaction. In this case, when we have elementary steps, we have substances that are neither products nor reactants. They're called intermediates. So, nitrogen trioxide in this case is the intermediate for this reaction. The rate mechanism, again, then, is a series of elementary steps, and the sum of those elementary steps has to equal the overall reaction. We've shown in this case it does. And the mechanism must agree with the overall rate law. The overall rate law is determined experimentally, and so from our elementary steps, we have to be able to come up with a rate law from the rates of each elementary step in some sort of combination or other. So back to this reaction, we have the elementary steps and we have the rates for each one. And when we have multiple mechanism steps, one of them is going to be slower than the other. The slowest step determines the rate of the overall reaction. And the rate law for that slow step then becomes the rate law for the overall reaction. So in this case, the rate law for the first step and the overall rate are the same, so that means our first step is the slow rate determining step, and the other one is, comparatively speaking, faster. All the elementary steps are theoretical. They're based on the rate law. They're based on the reaction. And you can't prove correct the mechanisms, so there may be multiple mechanisms for a particular reaction. You can only prove a mechanism is wrong. Let's take a look at a couple of examples. We're going to start with the reaction 2 nitrous oxide plus oxygen goes to 2 NO2s. Experimentally, we find the rate law has been determined to be K times the concentration of NO squared times the concentration of oxygen. We have a mechanism of 3 elementary steps that has been proposed, and our job is to figure out if this mechanism matches and agrees with the rate law experimentally determined. So the first thing that we're going to do is we're going to figure out what is the rate law for each elementary step. So we have rate is K1 times NO squared. Because the first reaction is reversible, and we know that because we have a two-headed arrow, we're going to write the rate law for both the forward reaction and the reverse reaction because they are equal. The second step has been identified in the mechanism as being rate determining, so we're going to make sure that that rate law in some shape or form can get to be agreed with the rate for the overall reaction. Not looking good so far, but we might be able to fix that. Let's look at the third reaction. N2O3 and N2O2 and O are all intermediates. In my rate determining step, I have N2O2. I need to get rid of it. So the other place that occurs is in my reversible reaction. So what I'm going to do is I'm going to write the rate law for that first reaction in terms of the concentration of N2O2 and see if I can do some substituting. So algebra simply lets me rearrange that equation, and now I have something that I can put in the rate determining step, elementary step, in place of the concentration of N2O2. If I do that, it looks like I might get my overall rate law. So let's take a look at that. All right, multiple colors here. I apologize, I missed step. There should be no 2 as a subscript there, so it's now gone based on the rate law for the first reaction. I've simply taken the concentration of N2O2 in my second rate law and replaced it with this thing here. And now I've got a mess of K's, but I have NO squared and I have O2, which is what I want. But this is just the product of 3 constants. So I can multiply them together to get a new constant, and then I get the rate equals some new constant K times the concentration of NO squared times the concentration of O2 by substituting and combining the rate laws of elementary step number 1 and elementary step number 2, and I get the rate law for the overall reaction. What this tells me then is that this mechanism does agree with the overall reaction. Here's a second example. Let's take a look at this. Mechanism is provided. We're supposed to figure out which is the rate determining step. So we have the rate equals the K constant times NO2Cl. So it's first order. So let's take a look at and come up with the rate laws for each of the elementary steps. First one looks pretty good. Let's take a look at the second one just for comparison. Both of them had NO2Cl in them as reactants, but the second one also has chlorine atoms as a reactant, and so its rate law must include that as well. So what it tells us is the first elementary step is our slow step and our rate determining step. And for mechanisms, that's what we're going to be doing, is determining which is the rate determining step, or determining if a mechanism is appropriate and fits with the overall rate law. You will never have to be able to create mechanism steps on your own.